When you took Algebra 2, you studied a bunch of different types of functions, kind of like we've already done. We've done rational, we've done polynomial. But every time that you learned about a new type of function, oh, there's a cricket in here. Does anybody want to get it? All right, cricket taken care of. Let's hop back into it. I don't remember what I was exactly saying before I got distracted by the cricket, but in Algebra 2, you learned about different types of functions, and then every time you learned about one, you transformed it, meaning you moved it around the graph. You stretched, shrunk, translated it, dilated it, reflected it. Are these all words that sort of sound familiar? Yeah, let's review all of that. That's what our topic is over today. Except we're not going to necessarily be transforming functions all the time. We're going to be transforming intervals and coordinate points and domains and ranges. But the concepts are still the same. Ooh, I ran up the stairs after throwing that cricket outside. I'm a little out of breath. That's so sad. But the concepts are all the same. So what you learned in Algebra 2 is the exact same thing we're going over today. When you have a function that you have added a number to at the back, so you have a function and you do like +5, that is a vertical translation of the function, meaning you are moving the graph either up or down that particular number of units. Okay, so we're highlighting a lot on this French page. This becomes like a nice little reference. And ooh, look, color-coded up at the top too with the pink. Nice. When you are vertically translating something and you have a positive number, it goes up. So plus k is going to move a graph up and minus k is going to move a graph down. Does that sound familiar to us? Yeah. Fabulous. Like I said, the concepts have not changed. So in my example here, we have this piecewise function that kind of looks like a square root. It's fine. It's named f, and we are going to subtract 2 from it, which means every single coordinate point in this graph moves down 2 units. That's way more than 2 that this one is moving down. You get it. It's moving down. It moved 3 units. It's just that's a typo on a graph. My bad. Do you see that? It's like actually moving 3 units down. Whatever. You get it. It's moving down. That's the whole point. Okay, cool. So that happens whenever you are adding a number at the end. Let's say now you're going to multiply a number in front of the function. Multiplying a number in front of a function, we're going to call a vertical dilation. Last year and every year you learned about transformations, you called that a vertical stretch or shrink. I don't really need you to tell me whether it's stretching or shrinking. I need you to tell me that it's dilating, which means stretch or shrink. And it's going to stretch or shrink by a factor of the absolute value of a. Okay, if that number is a big number, like say there's a 5 in front of it, it's going to stretch, so it's going to get like taller. If it's a fraction, like a true fraction, like 1/2 or 1/3, it's going to get wider because you're going to squish it down, you're shrinking it. But I don't really need to know whether it's stretching or shrinking. I just need to know that we're dilating it or we're multiplying by a number. There's a note here, though, that's super important. If a is less than 0, meaning if that number is negative, you've actually reflected that across the x-axis. In Algebra 2, you consider that a different transformation. For me, it's all a part of vertically dilating something. Vertical dilations include the flips over the x-axis, how your happy parabolas become sad parabolas. So if we see in this graph right here, we've got a -2 in the front of f of x. So we take the square root looking function and we're going to flip it over and stretch it or multiply the outputs by 2. So watch this one. Oh, wrong color, Miss Quigley. This one flips over and then gets multiplied by 2. So we go from +1 to -1. Multiply by 2, now it's at -2. This point right here is at +2, so it flips to -2, and then we multiply by 2. -2 times 2 is -4. So it flips and it stretches, meaning this is our dilation. Now, both of these two transformations are underneath a heading on the side that says what? What does this say on the side? Oops. The range or the outputs. These two transformations affect the outputs of a function. So if we're transforming something that has to do with the outputs, aka the y values, these are the transformations that affect y values. They do not affect x values whatsoever. They do not affect the domain. Okay? The two transformations that affect the domain are the two transformations that occur inside the function itself. Do you see the difference here? How x plus h and b times x are inside the function? They are going to affect the domain of this function. This is how we're going to differentiate our different transformations and what we have to apply to either coordinate points or intervals on our graph. Now let's talk about these. So f of x plus h, since that plus h is inside, we know it's affecting the inside or the inputs of the function. That is a horizontal translation of negative h units. This is the one that goes the opposite. Meaning, if you see negative h in the equation, you are moving to the right. It's the HIO, horizontal, inside, and opposite. If you see plus h, it's moving to the left. Normally, positive things go right, so the fact that this is on the inside, it's the opposite, HIO, horizontal, inside, opposite. But more so, I want you to change that I and inside to inputs. Horizontal affects the inputs, and they go the opposite direction. We're all about the inputs here. So if you notice in our example graph right here, let's see if this one actually moves the right way. This one says plus 2 on the inside, which means my graph should be moving to the left. I take every coordinate point and I move it to the left 2 units. Do you notice that none of the output values changed? We only changed the input values because it's on the inside. It affects the inputs only. Our last transformation is a horizontal dilation. A horizontal dilation is a multiplication on the inside of the function. Same thing as vertical dilation, that it's multiplied by something. This is also, in my opinion, some of the most challenging ones to think about because it is on the inside, it affects the inputs, and it's the opposite, which means we're multiplying by a factor of absolute value of 1 over b, the reciprocal of the number that you see. And then because we're combining what last year you separated reflections and dilations, we are not separating them in this class. If b is less than 0, that's a reflection over the y-axis. So it flips over the y instead of flipping over the x. Okay, these are affecting the inputs because they're inside the function. So if we look at our example graph right here, this one is just times negative x, negative 1, right? It's just going to reflect. So all that I've done is taken all of the input values and reflected them. This input value right here was 1, so it becomes negative 1. This input value was 3, so it becomes negative 3. This input value was negative 2, so it becomes positive 2. We're changing just the input values. We're not touching the output values at all. That's the big difference from what you've done with transformations in previous classes to this one. Bless you. Previous classes, you've just moved all of the functions, watched it go left, right, up, down, stretch, shrink, all that good stuff. Great. We're actually looking at coordinate points, intervals, and domains and ranges to transform them in my class. But this reference sheet up in the front is going to be very helpful. I feel like I've missed some. Okay. Let's highlight the stuff at the top too, just so it's all color-coded for you. This one for me was blue, and then this one, blue, purple, and then green. Look, it's all cute and color-coded. This is now your reference sheet for transformations. We have the transformations that affect the outputs that are on the outsides. We have the transformations that affect the inputs that are on the inside. Knowing the difference is important. Yes, sir. The B is in purple, yes. Yeah, I think I said blue, but I meant purple because I did purple down here. I swear I know my colors. That's debatable. Hey now. I'm going to give you a second to catch up coloring because I know that's a lot, and we're going to meet on the back page. In my class, we're going to be working on transforming intervals, coordinate points, and using functions to write other functions. So for example 1, we're going to use the graph of f, which is here in the picture. This is f. And we're going to use the equation for g, which if you notice, g is a transformation of the function f. See how f of x is in here? We're transforming this function to make g. We're not going to graph g. We're just going to talk about all the properties of g using the transformations. Let's highlight what each of these are. If I've got a 2 in the very front, what is that called again? Vertical dilation. I'm going to use VD because I'm lazy. Vertical dilation, and that means I'm going to multiply by 2. Okay, if I've got a -1 on the inside, what transformation is that? Oh, yes, what is it called though? Starts with the H. Horizontal, bless you. Horizontal, bless you again. Horizontal translation, HT, because I'm lazy, so sorry. You did tell me this, which direction is it going? To the right one. I'm going to put +1 because to me, outside of transformations, right is a positive direction. And that will be very helpful for what we're doing in a second. Then we have this +3 at the very back here. What does +3 outside the function do? Vertical translation, what direction? Up 3. I'm going to use plus as up because plus is a positive direction. We've identified the transformations we're applying to the function f. We could graph this thing. We're not going to. We're just going to use these transformations to write the attributes of g. For example, we're going to find the domain and range of g, not of f, of g, of the transform function. To start this off, though, I guess I do need to know the domain and range of g, of f, so sorry. Remember that domain is the list of input values and range is the list of output values, or you would have called that the x's and the y's. So if we're looking at the graph of f, we could write down that the domain of f, so D for domain, little bitty f for the fact that this is the domain of f. What's the x value that this graph starts at? -5. What's the x value where this graph stops? 5. Why did I choose to use brackets here? Because of the closed circle. Amazing, great. Okay, but we want to take this domain and we want to transform it for g. Domain is all of the x's. It is all of the input values. Which of these transformations affect the input values? Input values? Inside is input. The only thing that's inside this function is what? Horizontal. So what we are going to do is we are going to transform this by doing that horizontal translation of +1. We're going to take these input values and we're going to create the domain of g by adding 1 to both the first and the last coordinate in my domain and range. This is now the domain of g. We have taken the horizontal translation and applied it to the input values. You had a question?
Yeah, what does DS mean again?
df, the domain of f.
Okay.
It's like a subscript of f. Since I'm talking about two domains, I needed to tell you which one was which. So domain of f and domain of g. Okay, pause before we ask more questions. I want to do one more. If we're doing the range of f, how low does f go? How high does f go? 3. Why did I use closed, or the brackets? I just said the answer. Why did I use brackets? It's closed. You don't see an open gap there. You know the graph actually touches there. Okay, which of my transformations affect the output values for the range? Vertical dilation and both of the verticals. Very good. So I'm going to do them one at a time. You have to do dilations before you do transformation or translation. So I'm going to first vertically dilate these numbers, which means I'm going to multiply these numbers by 2. So on the road there, this is not the final answer, but we're going to get -6 to 6 because we have multiplied these values by 2. But I have another transformation to apply to this, which is my vertical translation. When I do this vertical translation, it says +3, which means I'm going to add 3 to both numbers, giving me that the domain of g would be -3, 9. You're so right, that is the range. Hee hee. The range of g is -3 to 9. Now, a question you might be asking, is this notation required? No, this is my thinking notation. This is how I think. We're going to do it piece by piece. The first step is to vertically dilate the range. So this is me vertically dilating it, times 2. And the next step to finish is to translate it. So that's my +3. So no, it's not required, but that's how I think. Does anybody have a question before we try again? Yes, ma'am. To start, like the range of f. Range is the output values that I use. So I look how low the graph goes. This is the lowest this graph goes, right? -3. How high does this graph go? 3. So the range of f is from -3 to 3. But then I, for g, need to vertically dilate it, which means times 2. So I multiplied -3 and 3 times 2. and then I have to vertically translate it, so I add 3 to both numbers. Yes? We followed. Okay. For number B, it says the point 4, 2 on f of x transforms to which point on the graph of g of x? So this time we're transforming a coordinate point, not a domain and not a range. In coordinate points, remember, they are always x, y, which means they are inputs, outputs. So we have to do the correct transformation to whatever input or output we have. If we start with the number 4, 2, let's first take care of the input values. So I need to horizontally translate this by adding 1. I'm moving the HT on top of the arrow because I'm realizing I'm writing in color, but you writing not in color might not be able to see that. We need to just add 1 to the input values. I did not add 1 to the output values because horizontal translations only affect the input values, so the x's. Do you see that? When I go to do the vertical dilation, should that affect the inputs or the outputs? Outputs, which means this becomes 5, 4. 2 times 2 is 4. Now I'm going to add 3 for the vertical translation. Do I add that to both the x or the y? Just the y, because we're only affecting the outputs for vertical translations. So the gain here is knowing which input or output you're talking about to begin with to know which transformations you need to apply. Questions now that we've seen 2 examples? Yes?
So for the HT, you just multiply it
For the HT, what I'm doing on HT is I'm adding 1 to the inputs. So we went from 4 to 5. On vertical dilation, since it's the number 2 in the very front of my functions, I'm multiplying by 2. And for the vertical translation, I'm adding 3. Does that make sense? Okay. Can we try another something? Okay, let's talk about on which intervals g of x is increasing. To talk about where g of x is increasing, we need to first know where f of x is increasing. Okay, here's a note to yourself that might be helpful to write down. G of x is going to be increasing when f of x is increasing. So we need to know in our function where f of x is increasing so that we can transform that to the g of x function. So let's first talk about where f is increasing. In this function up here, a nice review of increasing, decreasing. Where is f of x increasing? You're going to not want to highlight yours because you can't erase highlighter, but here's what y'all are telling me in case you're like, what are they talking about? From -4 to -1. 1 to 4. Okay, yes, that's the places where this is increasing. Okay, I'm going to erase this because we're going to want a clean graph for just a second. But we see that that's where it's increasing. So we said, you guys told me, this is increasing from -4 to -1 or from 1 to 4. Right? Now, why did I use parentheses here? Because it's an interval of increasing, decreasing. We always use parentheses for those. Yes?
What is the wording?
It's a shorthand for increasing, INC.
Oh,
Increasing part of F.
If we
Yeah.
use notation like that on the AP test, would it be allowed?
I would not. It's not wrong, but you don't know what the reader understands that to be since it's not like worldwide usage of notation, right? You don't know if your reader is coming from London or Saudi Arabia. What if they don't use notation like that? You want to use words, like writing it all out. Does that make sense? Okay, thank you for asking. But now we want to take this interval where f is increasing and we want to transform it to the g of x function. These are all x values that you wrote down, which means you are only going to use transformations that affect the inputs. What's the only transformation we have that affects the input? our horizontal translation, which means we are going to add 1 to every single one of those numbers because all of those numbers are input values. So our G increasing interval is from -3 to 0 or from 2 to 5. So again, if you notice, we've had to use different transformations each of these questions. On the one that talked about domain and range, domain is your inputs, so you use the inside transformation. Range is your outputs, so you use the outside transformation. A coordinate point is both inputs and outputs. So we had to do all of them, but only to specific numbers. Yes? For this one, we always answer intervals of increasing, decreasing with just x values, just inputs. So we only do the inside transformations. We don't have to do the outside transformations because those are not outputs. They're just inputs. Additional questions, comments, concerns? Not yet? We'll ask later. The last questions on here are going to be like the ones I'm going to have you practice outside of class. This one says find G of 0. Well, G of 0 means that the x value that I'm using is 0. So if I just like old-fashioned function notation, start plugging 0 into the G function, here's what it's going to look like. 2 times f of 0 minus 1 plus 3. Whoa, where did all of this come from? Yeah, look at the top of your paper. The original equation says g of x is 2 times f of x minus 1 plus 3. So instead of x, what am I putting there? Amazing. Let's start doing some arithmetic. We start on the very inside because PEMDAS tells me to deal with the parentheses first. What is 0 minus 1? Amazing. Great job. We're on a roll. Now I have to actually evaluate this function because f of -1 is telling me to evaluate the f function at -1, which means it's time to read the graph. When you look at your graph and you have an x value of -1, we're looking right here on our graph. What is the output when the input is -1? Yeah, it's 3. So if we read this graph, we know that we have an output of 3 when the input is -1. So in the spot of f of -1, I can put the number 3. Because I read the graph to find that f of -1 is 3. Well then look, that's just numbers left. We love that. 2 times 3 is 6. 6 plus 3 is 9. So you plug the number in and transform it using the f function to apply it to the g function. Are we okay? What if I give you a different piece of information? I gave you an input number and I got an output number. What if I give you the output number and ask for the input number? No big deal, we're going to handle it. Here's what it says. It says g of k, which means I'm going to plug k into the regular function. 2 times f of k minus 1 plus 3. That should be equal to -1. I know that's a double equal sign. We're going to kind of ignore this part. Okay? But to write it, it's just easy to see. Okay. In fact, I am going to ignore this part just to make it easier for you to see. This is the function I'm solving. We need to get this k by itself. We're going to solve for k. To get the k by itself, we first need to isolate the f of k minus 1. So I need to get this plus 3 to go away first. How do you get plus 3 to go away? Subtract 3. All right, subtract 3 from both sides. You get -4 on the right-hand side. There's one more step to do to isolate the f of k minus 1. What is it? Divide by 2, the number in front of f of k minus 1. So I get -2. I've just solved this equation to isolate f of k minus 1. Now, here's the interesting part. f of k minus 1 equal to negative 2 is telling me to look at the f function for where it's equal to negative 2. That's an output value on f. So when I go look at f equal to negative 2, here's where f is equal to negative 2. What's the input value there? Negative 3. Do you see the difference in these two? We'll focus on the difference actually in a second. Let's finish this problem. So what we're saying here is that f of k minus 1 equal to negative 2 is just like saying k minus 1 should be equal to negative 3. Then you just solve for k. Add 1 on both sides, boom. K is equal to negative 2. Now, whoa, wait a second. Let's make sure we understand where these numbers came from and the difference between how I read the graph for D and how I read the graph for E. When we were looking at D, our input value was negative 1, so we gave an output value of 3. So looking at your graph, when x was negative 1, the output was 3, so this whole thing becomes 3. This one, I know the output value is negative 2. What was the input value when the output was negative 2? Negative 3. And you can finish solving. Questions, comments, concerns? No, not yet. Okay. Let's try another question. So we're going to start at a different, whoa, what? Words. We're going to start out with a different equation. And we're going to follow some of the same ideas here. Okay, so if we were looking at this one, we first start by noticing that H this time is a transformation of F. So here's F. It's the same graph. What are the transformations I'm applying to F to create H? Vertical dilation of what? Vertical dilation of negative 2. If you want to think about it like this, it's a vertical dilation of 2 and a vertical reflection, or reflection over the x-axis. But if we just say it's a vertical dilation by negative 2, you know that it should flip over the x-axis, because it's a reflection as well. What else is happening here? What's this plus 3 doing inside the function? Horizontal translation. What is the numbers I should write? Minus 3, because this should move to the left 3. Left is a negative direction. What's the last transformation? Vertical translation, what direction? Down 1. So vertical translation, down 1. Okay. Let's just see if we understand separating what happens to what. I want y'all to do A, but just A. Don't move on to B yet. It's going to ask you again to find the domain and range of H. So start with the domain and range of F and apply the correct transformations. Let's see if we got it. Okay, I'm loving what I'm seeing around the room, but I'm seeing the same thing every time, and it's because we're following instructions a little too well. Okay, if I was finding the domain and range of H, I would start off with the domain of F. The domain of F, we found this before to be negative 5 to 5. And we apply the transformations that affect input values, because domain is the input. The only transformation that I have that affects the input values is this horizontal translation of minus 3. Whoa. I don't know what happened to my voice just then. Of minus 3, which means this ends up being negative 8, 2 for the domain. Let me make that look nicer. For the domain of G, it is from negative 8 to 2. I'm seeing that one kind of across the board. We did great. Awesome. Amazing. And here's where you're following instructions almost too well. The domain of, not G, oh my goodness. The domain of F is from negative 3 to 3. And here's what everybody did, and I love it. You said, all right, we have to vertically dilate this, which is multiplying by negative 2. So almost everybody I went around and saw did this, because we multiplied those numbers by negative 2. I love it. Thank you for following instructions. However, intervals are always in number order. Is 6 smaller than negative 6? No, so this interval doesn't make sense. If you were typing this into a calculator, into a computer, it would be like error, something's wrong, because our intervals have to be in number order. So even though it doesn't look like these numbers switch because they happen to be the same exact number, it is -6 to 6. We did multiply by -2. We just still have to write the interval in the correct order from smallest to largest. Yes? But then I saw everybody after that, even though the numbers were flipped, you correctly did the vertical translation, which means that the range of, oh my gosh, I just realized I put a G right here too. The range of H is from -7 to 5. So a lot of us just had those numbers flipped around because, again, our intervals have to be in number order. But thank you for following instructions. Besides flipping those numbers around, I feel like the most part we got that, yes?
Yeah.
Okay, great. Here's going to be a challenge question for you. On what intervals is the graph of H concave up? What does concave up look like? Show me with your hands. Fabulous. I want to know where H is concave up. Where is F concave up? -5 to -2 and 0 to 3. I agree. Here's the thing though. We are transforming this graph with a vertical reflection. So is H going to be concave up the exact same places where F is concave up? No, because we're flipping it all over. So in fact, because of this reflection, H is going to be concave up when F is concave down, because you're flipping it over. And again, this is due to the reflection. Okay, since we're reflecting this graph, it's one of the transformations that we have to remember that not necessarily for this one is concave up going to be in the same spots. In the problem we did on the front page, increasing was at the same spot for both functions because we didn't flip that function over. We flipped this one over, so we have to think about that before we do the transformation. So when I'm doing this, I'm going to look for where F is actually concave down. You guys have already told me where it's concave up. So where is the intervals where it's concave down? -2 to 0. Or where else? Concave down on F. 3 to 5. Okay, that's the places where F is concave down, which means those are the places for H where it is concave up, except we're also transforming it again. So not only do we have to rewrite this as H being concave up, we do have to horizontally translate this because these are all X values. So the horizontal translation of -3 is going to apply to all of these numbers, which means this would end up being -5 to -3 or 0 to 2. Those are the places where H would be concave up. So it's still comparing one graph to another, just talking about its specific qualities and characteristics in a transformation. Whoa.
So one of the intervals is the same as right?
Say that again?
Well, no, it's slightly different. Never mind.
Oh, you're saying like the -2 and 0 and 2? Yeah. Okay, C and D are like repeats of the last two problems from the front page. What D and E on that one. Can you guys try C and D here? I want to see if you can apply that knowledge from the other side of the paper to these problems before we go on. C and D are yours. You got it. Okay, I'm sorry if I'm cutting off your thinking, but let's go over them. For most part, I think we're either, like I said, stuck or ready. So for H of -3, that's an input value, so I plug it in. H of -3 would be -2 times F of -3 plus 3 minus 1, which is -2 times F of 0 minus 1. When you go read your graph, we need a number for F of 0. But when I do F of 0, meaning the input value is 0, what's the output when the input is 0? 1. Because if you go look at the graph, it's equal to 1 when x is 0. So I can go replace that with the number 1. This would be negative 2 minus 1, which is negative 3. Good? For D, this is no, it doesn't read exactly like problem E on the front page, but it is the same thing because I'm giving you an output, so you put it on the outside. You put it equal to the function. Yes? I went too fast? Okay. I'll go back to it in a second for you guys. Okay, so this one, I'm doing h of x, which is negative 2 f of x, I lost the equation, plus 3 minus 1. That should be equal to 5. And I have to solve for x, which means first isolating the f of x plus 3 by adding 1, to both sides, dividing by negative 2 on both sides, and then reading the graph to figure out what the input value is when the output value is negative 3. What is the input value when the output value is negative 3? Negative 4. So the input of x plus 3 should be equal to negative 4. If you're like, what? The output value being negative 3 means I'm looking on the y-axis for negative 3. What's the input value when that happens? Negative 4. One last step to finish solving, because we still want the x by itself. We subtract 3, we get negative 7. Okay, as additional practice, I have this last problem here that has values from a table instead of from a graph. Same vibe though as C and D. Let's get some additional practice in. We have a new function and we have a new table of values. So you're using the n of x function and the m of x function here. I want to see what you can do with a table. It's the same kind of vibe as the ones we just did now that we saw an additional example of them. Let's see if we can do all 3, A, B, and C. You got this. Yes, I can. If we're doing, you can go, Luke, if you want. For number 4a, we're doing n of 0, which means the x value is 0. So n of 0 is equal to negative 3 times m to the 2 of 2 minus, of 2 times 0 plus 5. Okay, this vertical dilation of negative 3, a horizontal dilation of 1/2, and a vertical translation of 5 is what we're applying here. So if we start doing this, this is negative 3 times m of 0 plus 5. If I read my graph though, or the chart this time, the chart's going to tell me that m of 0 is equal to 3. So I can replace m of 0 with the number 3. So this ends up being negative 9 plus 5, which is negative 4. Did y'all get negative 4? Yeah. Yay, awesome, great work, love it. For the next one, same vibe, we're going to just this time have the input value be 4. So n of 4, again, means the input value, or what I'm plugging in, is the number 4. So that means I have negative 3 times m of 8 plus 5. Well, m of 8, again, if I read my table, m of 8 is equal to negative 12. So this would be negative 3 times negative 12 plus 5. Negative 3 times negative 12 is positive 36. 36 plus 5 is 41. For the last one, and this is the one I'll slow down on because I think this is the one where people have the most questions. This time I gave you an output value, so you don't plug it in. You set the equation equal to that. Negative 3m times 2k plus 5 equal to negative 10. The reason why I'm using k instead of x is because the question tells me to use k. A different variable letter, it doesn't matter. So we're going to subtract 5 from both sides. That's negative 15. We are going to divide by negative 3 on both sides. That's 5. Then we read our graph because we've got m isolated. When m is equal to 5, what is the input value? 4. Oh, just barely can't see it. When the output value is 5, the input value is 4. So I know that this 2k, the input value, should be equal to the input value of 4. And voila, just divide by 2 on both sides, you get the answers 2. If we got stuck on C, we probably got stuck on the m of 2k equal to 5-bit. Remember, that's an output value, so you look at the outputs of m to find the input that creates 5. Yes? All right, if you look at your worksheet for today, it's a lot of questions exactly like what we just did with the table. You're going to use that table for the entire thing. There is also an answer bank down at the bottom so you can check your work as you go.